like to explain about the experiment that we're going to do. The experiment that we're going to do is single degree of freedom torsional vibration. I will explain about the introduction of vibration. Vibration have two concepts, which is free vibration and forced vibration. Free vibration is no external force as supplied to the system, and the other one is forced vibration, which is we have an external force acting on the system. In this experiment, we use forced vibration, which is we have to supply a load, different loads to the system. This is the working system of the single degree of freedom torsional vibration. We will apply a different mass, which is 100 gram, 200 gram, 300 gram, and 400.
Assalamualaikum, my name is Nur Azina binti Abdulini, MA 11037. Okay, for this experiment, there is a few components to take note about, which is the flywheel, the mass, the length of rod, and the LVDT sensor. Okay, there is also a variable data which is also important to take note inside this experiment. Okay, the first is the distance between the LVDT sensor and the center of flywheel. And the second one is the mass and diameter of flywheel. And the third one is the distance between the mass and the center of flywheel. To determine the stiffness value, the 100 gram mass is applied at the end of the arm. A synchronized LVDT will be connected to the daisy lab. The change of displacement of the wheel will be recorded through the LVDT sensor, and so through the LVDT we can calculate the data of this experiment. To determine the natural frequency, it will be setting up by the daisy lab. Natural frequency can be determined straight away through the daisy lab. This will explain more by my team members.
Okay, Assalamualaikum, my name is Ahmad Badizaman and my ID number is MC11052. So I will proceed my group presentation. Okay, for my part is I will present about the apparatus, and we go into the hardware, software, and the lab. So for the first thing, we need to set up all the apparatus as shown here. So this flywheel, and we connect to LVDT. So this sensor will connect to hardware national instrument. Okay, this hardware national instrument we collect all data, the motion from the flywheel, the sensor by LVDT into the software by USB cable provide. So after we set up all the hardware and apparatus, we open the software, national instrument software. Then we set up this software. So after we get all the setting, then we test it by run. So the condition is good, and then we can proceed to our software, that is daisy lab. Okay, for the daisy lab, we need to synchronize the software from the national instrument software. Then we also need to change the input for this module. Okay, there is my task now plan. Okay, for this module task, we select the task name that we get from our national instrument software. This is for my group, my voltage task. Then in this lab, we need to calibration. This calibration is to convert voltage into displacement. So we do the calculation by some experiment, and then we get the value y-intercept and intercept. So we set in here this value. So after we done the value, we can get what voltage and what distance to convert. So we proceed to the raw data. Okay, this raw data. Okay, before that I will run the that. Okay, this.
Hi guys, my name is Muhammad Afiq Shahid. My ID number is MH11096. Right. For this experiment, I will present about the result and the calculation. First of all, come here. Right, guys, this is the result and the calculation of the experiment, which is the calibration data, voltage to displacement. Right. What you guys can see from here, this is the table for displacement Y versus the voltage V. Right. From this table, we can continue to create a graph of voltage versus displacement. Right. The next part is we need to measure based on the data given. We can measure the decay rate determination. Right. From this, you can see the diameter of shaft used is 6 mm. Length of the shaft between supports, which is L, 54.3 mm. The flywheel radius 50 mm. Hanging disc and rotation axis distance, which is Z 264 mm. Mass of hanging disc. We use many different weights of the mass hanging disc, which is 100, 200, 300, 400 gram. The next thing is the flywheel mass, which is 423.5 gram, and the last thing is strain of the shaft, which is G 77.2 gigapascal. Right. The next part, which is to calculate the decay rate. Based on the formula given, we can calculate the disc mass. Based on the disc mass, which is 100, 200, 300 and 400 gram, this will answer the question, which is we need to calculate the decay rate. This is the answer: 1.9, 1.9101 for 100 gram, 0.4185 for 200 gram, 0.3963 for 300 gram, and 0.2016 for 400 gram. Right. The next thing is the damping ratio determination. The damping ratio determination, what we have here is the stress, the C, which is the formula is 2m stress, 2m sigma, and Z, which is C over 2. Right. From this formulation, we can calculate the damping ratio for each disc mass. The different weight of the disc mass will contribute to different answer for damping coefficient, which is C, and damping ratio, which is zeta. This is the table. Right. Right. This is the sample calculation for the damping ratio determination. Right. You can see from here, this is the calculation. The unit of the answer is in radius, and the zeta right here, the answer will get 2.7371. Okay. The next thing is compare the theoretical stiffness and experimental stiffness. Theoretically, the torsional spring constant or stiffness, also known as KT, is determined from the relationship between moment and angular displacement, theta, of the shaft. This is the formula, M naught equals to KT theta. Right. From this, we can create, we can use other formula to calculate the KT. This is the other formula. Based on this formula, we can calculate the KT like this. The sample calculation for any disc mass, the KT, which is 18.0787 Newton meter, And from this answer, we need to change into radian, Newton meter radian, which is 5.754. Right. This is the theoretically, and the next thing is experimentally. This is the formula: T equals to KT theta, and this is the addressing. The T is torque due to the hanging disc, theta is torque angle, F is this way, and R is the radius of the flywheel. Right. From the calculation, we can create a table. This is the table experimental result for torsional stiffness of each mass, in which original height for H0 is 49.2 cm, and this is the comparison between theoretical and experimental torsional stiffness. The mass, the different the different mass we use: 100, 200, 300, and 400. And this is the result for coefficient of torsional stiffness in experimental, mathematically, and this is the error between these two, experiment and mathematically. Right. For this table, this is the sample calculation. For example, we just use 100 gram. Angle calculate. DH 49.2 minus 49.0, and the answer is 0.2 cm. And then from this we can calculate the theta, which is 0.0076 radius. Calculating the force, 0.981 Newton. Calculating the torque, the answer is 0.00037 Newton meter radian. Experimental stiffness calculate KT, which is 0.0487 Newton meter radian. Right, that's all for me. I will pass the other calculation to my
Okay, Assalamualaikum. My name is Luqman Hakim, and my ID is MA11140. Okay, so right now I'm going to calculate the natural frequency experimentally. Okay, so for now, for the theoretical, the natural frequency formula is given as KT over I. Okay, so this is the natural frequency, this is the torsional stiffness, and this is the mass moment of inertia on the oscillating body. Okay, alright, so for this one, we can get the value of torsional stiffness from the formula of M0 is equals to KT theta. Okay, so we can rearrange this formula into KT is equals to M0 over theta. So this is a formula of KT. Substitute into here. So for I, inertia, the formula is mr squared over 2 plus mAh squared. Okay, so mr, this is the mass of the flywheel. Okay, sorry, m is the mass of the flywheel, r is the radius. Okay, and ma is the this mass, and h is the height. So we substitute all the value inside, and we got the value of I. Okay, so that is the formula for natural frequency. So for now, sample calculation for the natural frequency. Okay, let's say for mass of 100 gram, right? So we are going to calculate the I. The mass of flywheel times by radius squared. So it is going to be 0.4235 for the mass of flywheel times the radius squared over 2 plus MA is the mass of this mass. So we are going to using 0.1 kilogram times by 0.002 as the height squared. So the value here is 5.2977 times 10 to the power of negative 4. So this is the value of I. And now for the natural frequency is we're going to use this formula. KT is 0.0487 and the I here we have calculated, which is 5.2977 times 10 to the power of negative 4 square root. So it will give us 9.5878 radian per second. Alright, so this is basically how we calculate the natural frequency. Alright, then then we got this table where this mesh that we are using. This is the experiment value for natural frequency, and this is the mathematical value which is we have been calculated. Alright, so this is 400 gram, 200, 300 and 400 gram. And this one is the error between experiment and mathematical value that we have calculated. Alright, so 400 gram, this is the error, the difference actually between the experiment and mathematical, and this is the error for 200, 300 and this is the error for 400. Alright, so basically this is how we calculate and we get the result for natural frequency. Right, so that's all from me. Thank you.
Assalamualaikum. My name is Ahmad Sadikin Biasini. My ID is MH11083. Okay, I will explain about the discussion of this experiment. First of all, there is a difference between theoretical and experimental value. So, there considerably a low percentage of errors between theoretical and experimental values, depending on two main factors, which are tool wear. Firstly, it's tool wear. We can see this chuck and shaft have worn out due to continuous and long period of usage. This problem when the chuck is unable to hold the specimen shaft firmly and causes the degradation in results. Secondly, in theoretical cases, it considers only ideal condition, while only in real world, internal and external friction and other external disturbance are also calculated. Other than that, theories involved in this experiment is Hooke's law, which the torsional stiffness of the system from equation T equal to KT theta. It obeys the equation as long as it in its elastic region. Okay, for the conclusion, the torsional stiffness can be obtained using different amount of mass. Each diameter of the disc has different amount of mass. Next, for the conclusion, I will explain which the torsional stiffness can be obtained using different amount of mass. While each diameter of the disc increase, torsional stiffness of the shaft increase as well. However, the decay rate decrease when mass increase. So the natural frequency of this experiment is different, depend on 4 different masses, where the experiment for 100 gram experimental value is 23.2796, for 200 gram 21.6718, for 300 gram 20.2735, and 400 gram 19.6384 experimental value. So the difference in theoretical and experimental values due to consideration of disturbance of surrounding. So I repeat, the torsional stiffness of the system obeys Hooke's law as long as the shafts are twisted within its elastic range. Overall, this torsional vibration system is an undamped system since it has less than 1
The damping ratio is 0.4548. That's all. Thank you.